So
Okay.
we'll just proceed with Joel.
Okay. Thank you.
Okay.
So,
Can everyone hear me?
Joel, let me introduce first.
Okay.
Okay. So our next presenter is already known to PAASE. He's the PAASE past president. He's a professor of biosystems engineering at the University of Arizona, where he is this year's marking his 25th anniversary of service as faculty. He is currently the vice chair of the International Association for Vertical Farming, and the two focal areas of his engineering research in Arizona includes the design of vertical farming systems and the design of scalable bioreactors for cultivations of a variety of cell cultures for production of high-value bioproducts. I'm referring to Dr. Joel Cuello. Aside from being a world's renowned scientist, Joel is a multi-talented person. He's into arts. He paints and he writes poems. We witnessed this when we visited his house in Arizona during the time we worked on our USAID Stride Smart Mom project. He also loves nature and likes to do very exciting and adventurous activities. My friends, ladies and gentlemen, I'm very proud to present to you Dr. Joel Cuello.
Thank you so much, Dr. Dadios, and thank you for that kind introduction. Can everyone hear me?
Yes, we can hear you.
I'll take that for a yes. I'd like to thank as well Professor Ang. Professor Ang, thank you so much for that introduction lecture that you just provided. You just gave us really a kaleidoscopic view, a wide vista of all of these Industry 4.0 technologies and innovations. Some of them are already here. Some of them are already translated into reality, and a lot of them are still in the horizon. But really, you just underscore the fact that technologically speaking, we really are living in that period of human history that really is optimized for advancements in technology. So we really are living in a very exciting and interesting time period.
Thank you, Joel.
So my talk is on the exponential vertical farm powered by mobility and artificial intelligence. So what is vertical farming? This is NASA Kennedy Space Center in Cape Canaveral, Florida. I'm showing this picture to you because vertical farming really began with the space programs at NASA, as well as in the space program of the Soviet Union, when the Soviet Union was still the USSR, the Union of Soviet Socialist Republic. So this began around 1950s, 1960s, 70s. But I did my postdoctoral fellowship at NASA Kennedy Space Center in the 1990s, and that was made possible by the US National Research Council postdoctoral fellowship. And my assignment at NASA Kennedy was in a division called Advanced Life Support Division. And essentially, that means space farming. So NASA has this goal to be able to carry out and implement long-duration space missions that are manned, both on the moon as well as on the surface of Mars going forward. And for that to be really feasible, a manned mission on Mars or on the moon, the astronauts there will have to have a way of producing food on site. And of course, on the moon and on Mars, the environment is very harsh. You've got deadly radiation, you've got extreme temperatures, there's no oxygen in the air. And so with such a harsh environment, the only way that it's possible to grow food, particularly food crops, is in a controlled environment system. So this is an artist's rendition of a human colony on the surface of Mars. And this one could portray as well a chamber wherein the astronauts could be growing food crops. So this is not an artist's rendition. This is an actual biomass production chamber that was used for demonstration and experiments at NASA Kennedy Space Center in the 1990s. This is air sealed, so it's hermetically sealed. There's no leakage of air. These are plants that are being grown. This happens to be wheat, and it's being grown hydroponically, so there is no soil involved. The nutrients that are needed by the plants are provided using liquid nutrients solutions. So this is a hydroponic system. And the plants, of course, are securely anchored physically because in the environment of space, which is under microgravity conditions, if the materials or the plants are not properly secured physically, then they would just be floating in the air. So everything has to be secured in place. The plants are being supplied with lighting using high pressure sodium lamps because at that time, light emitting diodes were just starting to emerge and starting to be commercialized. So now most vertical farms, of course, are using light emitting diodes because they're far more efficient in terms of electricity use, as well as you can really control the wavelengths of the lights, red, blue, and you can tailor them to make it really optimal for the photosynthesis of the plants, would translate into optimal productivity of the plant, as well as the quality and morphology of the plant. So in this chamber, everything is pretty much controlled. The atmospheric pressure is controlled, the temperature is controlled, relative humidity is controlled, the light intensity is controlled, the daily duration of lighting is also controlled, the light quality is controlled, and so you can be assured that that would translate into the optimal or maximum productivity, yield, and quality of the crop that is being grown. So that is what is meant here by performance. You really are able to optimize the performance of the plant. But resilience as well, meaning to say, excuse me, this system really becomes dependable and reliable, and it's extremely consistent. So in other words, regardless of whether you are in the South Pole or the North Pole or the tropics or the temperate region, the performance of the plant will remain optimized. And of course, regardless of whether you're on the lunar surface or the Martian surface, the performance of the plants, the crops will remain the same at optimized levels, depending on, of course, whether you're able to control those environmental settings that are optimal for these crops. At the same time, this system is highly sustainable because it's using hydroponic systems, and using that, you save over 80% of water as required by the plants compared with open field cultivation. But of course, if we're talking about space environments, the use of open field cultivation is clearly out of the question. So the commercial development of vertical farms coincided with that, with the genesis of research of controlled environment systems by the space programs of NASA and the Soviet Union. This is in Japan. This was in 2007. I was invited by this gentleman here, Mr. Uchiyama, and he was a professor of a private university in Tokyo. And they invited me to visit this humongous vertical farming facility that they were building at that time. Japan is a pioneer in terms of the commercialization of vertical farms. And even today, Japan is the country in the world with the most number of commercially operating vertical farms. In Japan, it began in the early 1980s, and it's still, of course, happening today. So today, I just want to show you here a series of slides showing commercial operations of vertical farms. This one is the company Mirai, which is based in Japan. And now everyone is using light emitting diodes instead of high pressure sodium lamps. So these are white LEDs and these are red and blue LEDs. And again, everything is controlled. Imagine this to be a big warehouse that is filled with these shelves that are stacked one on top of another. And so you really are able to maximize crop production per unit area. This is another Japanese company. It's called Spread, which is in Tokyo, Japan. This is an American company. It's iBiotherapeutics that is based in College Station, Texas. They're growing plants, however, they're not growing the plants for food. They're growing the plants produce pharmaceutical products, specifically insulin in this particular case. This is back to food production. This is the company Plenty that is based in Silicon Valley in California. And this is Aera Farms that is based in New Jersey and the greater New York area. And they're now expanding globally as well, including in Abu Dhabi and the United Arab Emirates. This is a small vertical farm in Norway, in Oslo, which I visited last year. And this one is another big player in the global vertical farming industry. It's called Sanan Bio. I had a chance to visit them in China, but they do have a branch now in Las Vegas. And it is probably one of the largest, certainly one of the largest here in the United States. But anyhow, my focus on vertical farming is the design of minimally structured, modular, and prefabricated vertical farm. So essentially, this is like a Lego assembly where you're working with a standardized module or modular unit, and then you can combine them together in various geometric permutations and combinations. It so happens that one of the most commonly available modules out there is a shipping container. And so there's a number of companies now really that are specializing in converting or retrofitting shipping containers into vertical farming units. Here at the University of Arizona, my group has an old shipping container that we retrofitted to be a vertical farming demonstration system to be used by the students for training as well as for research. So these are some of my undergrad students taking a class that I'm teaching on vertical farming. And this is a shipping container that we retrofitted. We call it the Arizona Green Box. Here's an internal view of the shipping container. These are just conventional hydroponic growing systems. The one at the back, that's an original design that we developed and which we have a patent that is pending. All right, so we've demonstrated growing all types of crops in here from, this is chard, we've tried kale, lettuce, this is basil, and so on and so forth. So this one is an original design, but I'm not gonna focus on this because my talk is focused on automation. Although we're gonna be automating this actually this coming fall semester. All right, so there's a new paradigm in vertical farming that my group is introducing, and that is in reference to the current convention for vertical farm, which I refer to as the fixed vertical farm. So if you look at the existing commercial vertical farms today, they're pretty much fixed. So this is Aera Farms in New Jersey, and the shelves are fixed in place. They're not moving. And so to be able to access the crops in terms of planting, in terms of harvesting, a worker has to be riding this cherry picker, which is clumsy and which is inconvenient and could actually be unsafe for the workers. This is the one in Mirai, and clearly it's a fixed type of vertical farm. That's Aera Farms again. And here's a closer view of someone on a cherry picker trying to access the crops in the elevated portions of the stacked shelves in a vertical farm. So that was an inspiration for me and for my group to change the paradigm for vertical farming design, and that is to convert it from fixed to a mobile vertical farm. And we specifically designed what we refer to as a Go Vertical Farm. So here's a rendition of what a Go Vertical Farm would look like. But so essentially you've got these crops that are grown in the shelves provided with lighting, and you've got the nutrient system in here as well. And then this growing system is sitting on a mover robot. I don't know if you've seen a video of a warehouse for Amazon, but you've got these bookshelves kind of similar to this, sitting on mover robots, and then the robots are moving all around the place without any humans controlling them. They're programmed so that it's really convenient to move books and other materials around, or to access them, or to reclaim them from their storage facilities. So the Go Vertical Farm has two components. The first one is the Live Grow robots, which we refer to as the LG bot. So this is the LG bot. And the growing system may be generic. It doesn't have to be one of the patented designs. So here you've got the hydroponic tank, you've got the trays, the plants are growing on the trays, and you have a lighting system, which in this case is LDV. This is completely generic. This is not patented. However, the combination of any of these growing systems that you put on a mover robot, we have patented that. And in addition, we have our own patented growing systems. This is an iSprout green box. These shelves are actually completely collapsible for storage. So we're thinking ahead as well for future space applications, for deployment into space. You need to be able to collapse your materials and really minimize the volume for transport. Because if you have a bulky material, that's not ideal for transport into space. This is an I-incline green box, which is also original and we have patented. And there's another one, it's called the I-Abacus. But this is a rendition of where or how the LG bots could be arranged in a warehouse type of environment. And then the second component of that is the Automated Circular Operational Protocol, or ACOP. So essentially, it's a programming system where you're able to program the robots so that they would go in a circle. Initially, you've got the germination room in here, and this is the planting room. So the LG bots could be located here, and the germinated seedlings could be loaded onto them, either by humans or also by robots as well. And then from the planting room, the LG bots would proceed into the growing room. And then once the plants are mature and ready for harvest, they would then move into the harvesting room, where again, the plants could be deloaded or unloaded using humans or also other robots. And then from the harvesting room, it will proceed to the planting room for replanting again. So we're gonna represent the LG bot by this geometric figure here. So this is a side view of a potential warehouse where you're going to be housing your LG bots. So you've got first floor, second floor, up to nth floor. And the way to access the robots, the LG bots, is using an elevator. And of course, they can do that on their own. Professor Ang was talking about designing robots in a structured environment where you just program your robots to be able to do specific tasks in that structured environment. Or you can have an unstructured environment where the robots will be sensing and will be making decisions and plans, executing those plans, and learning in the process as well. That is very much applicable to this scenario as well. This is the top view. And let me see. All right, so here's another view. It look like this. These are the elevators essentially. And these are arranged. You may have an invisible line in here. So this could be the growing room, and this could be the other one, the optimizing room. But let me explain that clearer. So here's the planting room, here's the harvesting room, here's the growing room. So we start in here, the planting, the seedlings are loaded into the LG bots. The LG bots ride the elevator and they go into the growing room. But this could be designed in such a way that these seedlings here will be moving gradually from right to left. And the environment in this particular section of the growing room is optimized for maximizing the growth of the crops. So that by the time the LG bots reach the end of this section of the growing room, their growth is already maximized. So they move then to this other section of the growing room, and this section here could be designed so that the crops could be optimized in terms of their flavor profile and in terms of their nutrient profile. So they're already full grown, but their nutrients are being optimized. So by the time they get to this point here, next to the elevator, they're ready to get onto the elevator to the harvesting room for the crops to be harvested. But I just want to point out that, again, this could be taking place in a structured environment, or even though physically the environment seems structured, you can still program the algae bots so that they become social robots. In other words, each one is equipped with sensors. They can sense their environment, they can sense the plants, and then they can make decisions as to whether this algae bot, for instance, is ready to move forward, or it should stay behind until it reaches a certain degree of growth. So each bot now individually can make decisions by itself to make sure that the crops that they're carrying really gets optimized in terms of growth and in terms of flavor profile as well as nutrient profile. So these are the advantages of the Go Vertical Farm. So this is the new paradigm of the mobile vertical farm. So certainly mobility and automation, access, you don't need to send humans into those growing rooms because the algae bots can move on their own. Increased efficiency, labor efficiency for sure, safety of workers, clean operation, growth and nutrition optimization, machine learning and data analytics. Then at the same time, you could employ artificial intelligence to make sure that your crops are optimized, both in terms of growth and nutrient profile and flavor profile. So here's an apple, and this robot here is just a symbol of the algorithm. But essentially, an artificial intelligence algorithm using machine vision could decipher properties of this apple. Perhaps its sugar content, or its water content, or its nutrient content, or its color, and so on and so forth. And then those could be correlated with the particular environmental variables that were present during the growth of this apple. So in terms of temperature, relative humidity, nutrients, and so on and so forth. So artificial intelligence could decipher all of that and can do that correlation so that you can really optimize the crop. So in terms of crops that are grown today in vertical farms, such as this chard salad crop, you can optimize the yield, primary metabolites, proteins, lipids, carbohydrates, the flavor profile, and the secondary metabolites. These are the vitamins, the other nutrients, phenolics, and so on and so forth, that make crops healthy. And all of this could again be correlated with these environmental parameters such as humidity, pH, light, nitrogen, phosphorus, potassium, CO2, and so on and so forth. So with artificial intelligence having deciphered all of that, that setting can be applied, and presto, you got that optimized crop in terms of both growth and nutrient content. So vertical farming really is an exponential innovation. So innovation is value creation. And today in this industry 4.0, it's now possible to have exponential created value. And that is made possible using these 4.0 technologies that are available to us, which on their own also is advancing at accelerated pace. And this is true in terms of computing power, computing capacity, data analytics, machine learning, artificial intelligence, robotics, and so on and so forth. So all of these are now accessible to us, and they're ready for our deployment and integration so that we can really deliver value, created value that is exponential, that is growing exponentially over time. So this is related to Cuello's law, which I promulgated as a way of monitoring and measuring the exponential value of vertical farms. That is, crop productivity per unit resource use in a tech-dense vertical farm must double every 4 to 5 years. This really is an industry aspiration. So crop productivity per liter of water, per kilowatt hour of energy, per square meter of land, per kilogram nutrients, per cubic meter of volume, per hour of labor should double every 4 to 5 years, because we have access to all of these industry 4.0 technologies that are accelerating over periods of time. So anyway, I'd like to end by citing again that I'll be having this Department of Science and Technology Balik Scientist Fellowship in the Philippines. And where else to best appropriately spend that, but in the part of the Philippines that is most affected by our changing climate. So in November of 2013, that place was visited by Typhoon Haiyan, which is, I think, still the most powerful storm that ever made landfall in recorded history. And it devastated Tacloban and Leyte and Samar as well. But certainly, because the Philippines is a developing economy, it's better to design what I refer to as a frugal engineered vertical farm. So it's not as fancy as what's being designed here in the US and other developed economies, but something that is cheaper in cost, but certainly has enough capabilities to be able to optimize the crops in a way that they would not be at the mercy of the changed climate and the vicissitudes of the changing climate. So there's a way, of course, to optimize the indoor environment in terms of temperature, relative humidity, and other variables as well. And this would result in resilience and sustainability. So I'm privileged and honored to be invited to Eastern Visayas State University in Tacloban to do my Balik Scientist Fellowship. This is Dr. Aguirre, who is the president of the university. This is Vice President Aintik, who is the Vice President for Research. And of course, Alvin Colaba, our colleague at PAASE, really made this possible. And this is Dr. Luli Cruz, who's a PAASE member. This is Dr. Ann Villalobos as well. We have some De La Salle University gang members here. That's a term of endearment, which of course would be helpful as well. Will be helping us in this project together with Dr. Dadios, of course. And Professor Ang, of course, you are welcome, and I think we should invite you. So this is again the DLSU Federation. You'll recognize some of the faces here. And of course, we'll be collaborating as well with our next speaker, Ralph Becker of Urban Greens, since he's with a private company. And it's good to have this public, private, and academic partnerships. And I was just contacted actually by some researchers from UP Diliman, who's also, without my knowing it, they are also starting some research on vertical farming. And of course, we're open to collaboration. In Tacloban, there are farmers associations there, such as this one, Villa Consuelo Farmers Association. And they're starting to use this really rudimentary structure to be able to provide some partial control of the environment of the crops that they're growing. This is strawberry. And so they're really excited to work together with us to be able to, for them to implement and use this frugally engineered vertical farming modular units that we plan to design. Here's a second farmers association also near Tacloban. It's called the La Granja Farmers Association. And of course, in our Mock City, which is about 2 hours away from Tacloban, Mayor Gomez was a speaker yesterday in our special plenary session, and he's already indicated to me his interest as well in putting up vertical farming projects in his city. So we're happy to collaborate with him. And this is the governor of Leyte, Governor Mick Petilia. He's very business savvy. He has an MBA, which I really respect. And he is very instrumental in organizing those farmers associations and connecting them with the farmers. And so we really are going to look seriously into establishing indoor agriculture innovation economic zone in Leyte. And these are some of my scholars and graduate students at the University of Arizona. We refer to ourselves as bioimagineers. So thank you very much. I hope I didn't extended my time. Thank you. I'd be happy to answer questions in the Q&A portion. Thank you.
Okay, thank you very much, Joel, for that very interesting presentation. I'm sure a lot of audience now are asking questions in the chat. So maybe you can entertain them because we are we run out of time. So let us just proceed directly to the next speaker.